So just as usual, let us load our packages. Today we are going to use the tidyverse, just the tidyverse for now. Okay. So let us load our data. Go to files. We are going to load the physiochemical parameters, the one we used the first time. Physiochemical parameters, physiochemical, that's the one you're going to use today. Let's load our data. And as usual, we are going to configure our data and make it as we want it to look like. So here we're going to change our stations into factors, and we said our stations are 4, 1, 2, 3, and 4. And our months also, let's change them into factors. So we have May, June, July, August, and September and October. Okay, so those are our months. Let's convert these to be our DF. Let's make it a DF. All right. And then just copy here. Our clipboard copy there. Cancel that. Just paste it here. Oops, paste it there. Let's run it. Let's view it. There it is. Okay. Now today we are going to talk about, as I said earlier, we're going to talk about one-way Anova. Anova. One-way analysis of variance. So this is one way of hypothesis testing, and you want to check if the temperature, for example, here, the temperature for the whether the temperature was the same for the different months, whether the temperature for May was the same for June, for September, and for October. So we want to know that. So that's what we want to do. We want to know whether the temperature was equal, or there was a month where the temperature was different from the others. We want to compare the mean temperature. Therefore, because we're hypothesis testing, we're doing hypothesis testing, we can put our null hypothesis, our our hypothesis testing, our null hypothesis. We say that the mean temperature is equal for all months. And the null hypothesis, the alternate hypothesis, say that at least one month has a different mean temperature. So you can state your hypothesis as you would like, but the idea is that the means for all the months, or temperature for all the months, are equal. So the mean for month 1 is equal to the mean for month 2 is equal to the mean for month 3 up to the last month. And the alternate hypothesis is that at least one of those months has a different temperature from the rest. At least one. So it can be one or more. All right. So our data here, temperatures, our months here, you see the May, June, September. These September months are too long. Let's let's try to shorten the names of these months. So we are going to mutate. So let's create another data frame, another object called just df, just as it is, and take our data frame, and then let us mutate. There are things we call strings. I think this we're going to work with them later. Strings are just text, like we have these months. These months are strings. May, June, they are strings. They are just characters. They are strings. Therefore, we would like to change, to replace and change the names of these strings. Therefore, we are working with the column of month, and we are saying that the column of month is equals to, we say string replace. We want to replace all. Let us replace. So also in here you put the month again, and then in here in quotation marks you write the month that you want to change. You want to change the months that are long, like September.
Excuse me, Dan.
Yes, yes.
You said replace all and I can see remove all.
Oh, sorry. Yeah, it's supposed to be replace, replace all. Thank you. It is replace all. So here was September. Thank you, September. We want to change it to, also in quotation marks, let us call it sept. Let us run that, see if it works. Yeah, it has worked. Let me see whether it has changed. If you come here, the September has changed to sept. So let us do the same for the rest of the months. So let me copy this so that just copy that, and then so comma here. We'll do that for every month. Let me paste again. There are 3 months that I want to change. So which month do I want to change here? Another month that is long. It is August. Let's call it Aug, and October. Let's call it Oct. Let us run that, see if it works. Yes, it works. So let's see whether that has changed. Yeah, the months, yeah, they're changed. They're okay now, they are shorter, they're not as long as they were. You replace string, replace. This means strings. One day we'll talk about strings and how to replace them to add others and such like things. So we have our data frame here. Now we can do our Anova. Okay, now let's put it under, let's call it Anova. Let's just call it Anov. Let's put it under just saying Anova. The command or the function for for calculating Anova, it is AOV. That AOV, that is a command for Anova. Put into brackets, number 1, put the formula. So we want to check the temperature, tilde, put tilde against the months, the months, and our data is equals to df. So we are checking the temperature over the months and of the data, that is the df. So let us run that. Let's see what Anov says. Anov. Okay, so as you can see here, we have the formula that we have used, the data we have used, sum of squares. But to get a more detailed report, you use the summary command, summary of our summary Anov. Okay, it gives a more detail. So you have the degrees of freedom. We had 5 months. We had 5 months instead of 6. I thought there was 6 months. Oh yeah, it is 5 minus 1. Sure.
It's 5. Yeah.
It's 6 minus 1, so 5. Residues, these are like the variances of the mistakes. These are sum of squares. You must have done Anova by hand, and you calculate the sum total, the sum of squares, the sum of errors. You know that we have the mean squares. We have the f value here, which is 46. And we have the p-value here, which is 1.05 raised to the power of -9. So this is a p-value that is very, very low. And we test it against a p-value of 0.05. So 0.05 is a cutoff line whereby if our model has anything that is below the cutoff, that below the probability of 0.05, we say that we reject the null hypothesis. And if the probability value is greater than 0.05, we fail to reject the null hypothesis. We say that the means of all the months are equal. But in this case, the p-value is very low. This is 0.00001 or that. So it is very low, meaning that the mean temperatures for all the months were not the same. At least one month has a different mean temperature. So we reject the null hypothesis and we fail to reject the alternate hypothesis. Before calculating our ANOVA, we would have created a box plot so to visually see whether these means are different. So in base R, apart from we are using ggplot2, but I want us to use I want us to use base R functions to get the visualization. So we have a, let's say, box plot. Let's have a box plot of temperature across months, and our data is equals to df. Let's see what that does. So we have a box plot here, and you can see for real some months, these months are not, the mean temperatures for all the months are not the same. Therefore, there's something else you might want to know, or we would like to know what is inside this ANOVA. What is inside our ANOVA? So we put attributes. We take attributes of our ANOVA. What is contained in our ANOVA? So it has coefficient, residuals, and if you'd like to extract coefficient, residuals, effects, or any of these in any of the calculation that you might be asked to do, as you have seen here, we have typed attributes of ANOVA. So we can say ANOV, and then use the $sign to extract whatever we want. So maybe we want coefficients. The coefficient for the intercept was 25, and the coefficient for the month of July was 0.19. Month of June, for the coefficients, you might want to get the coefficients for the month, not the coefficient, but the residuals. You get the residuals. This we can cover later. And also, maybe we'd like to get how our model has its own way of modeling, how our model works, and that it is. So this is what has been working with. So this gives you the attributes, what is contained in your item. Now, after you've seen that your p-value is below the probability level that we would take, therefore we do what we call the post hoc analysis. Now you've seen that for sure some months have different mean temperatures, but now we would like to know which months have mean temperature. That's what we call post hoc, the post hoc tests. This you must do. Which months have a different temperatures? And here we use a command called a 2-key HSD command, 2-key HSD, and then you just write your item, which is ANOV. There it is. So what it does is that it does a t-test combining every 2 months, combining them together and seeing which months are different and which months have the same mean temperatures. And what you look at, it is a p-adjusted, the p-value. If the p-value is greater than 0.05, you say that the temperature for those 2 months is the same. And if the p-value is less than 0.05, you say the temperatures for the 2 months is different, it's not the same. Look here, July and August, the p-value is 0.789, so this is greater than 0.05, meaning that this July and August have almost the same temperatures. They are not, the temperatures for the 2 months are not significantly different. And for June and August, this is also greater than 0.05. Yeah, the mean temperatures are the same. They're not significantly different. May and August, this is a very low probability. Therefore, the 2 months have different temperatures. The temperatures difference between the 2 months are significantly different. So you can tell which months are different. And also you can visualize that by saying, let's plot the two-key HSD of Anova, of our function, of our Anova. See what happens. So it brings to you this this graph, this visualization. Let's see these months. What I want to do, you see, as you can see, these months are written. This is, I don't know what I call it. This is not. This is vertically, but I want them to be diagonal, horizontally. So let's do that. What you do, comma, plus is equals to 1. Let's see. Yeah, it's a little bit better. So as you can see, the months that are the temperatures, the differences in the temperatures are 0, meaning their temperatures are 0, they are equal. If you take the temperature for the month of July, for the month of August, the value is 0, so they are not different. They're not significantly different. For June and August, they are 0. But if you look for October and May, no. So these temperatures, and the difference between their temperatures is not equal to 0. Therefore, the temperatures of these 2 months, October and May, are significantly different. So you can see also here, September and October, these months, the differences, their mean temperatures are significantly different. September and June also. September in Kenya is when the sun is really hot. June is when it is really cold. And you can understand that. May and June, the same way. September and July, May and July also. So the only months that have the same mean temperatures are September and May. These are hot months in Kenya around also, and this data was taken in Lake Victoria, so you understand Lake Victoria, around that region it is quite hot. You have October and July. It's October, it's going to get cold, and July is when the cold is going away. October and August, the same case. So you can, this visualization shows you all that. And that's how you do your one-way analysis. All right. Okay. Now we ran our analysis of variance, and we said summary of that analysis of variance, and we had our p-value here. And as you can see, this p-value is less than 0.005. When you're doing hypothesis testing, we use a probability value of 0.05. So if your probability is less than 0.05, and you can see here this is less than 0.05 because this is 1.05 raised to the power of times 10 raised to the power of negative 9. So it is a very, very low probability. Therefore, it tells us that the mean temperature is not equal for all the months. So at least one month has a different mean temperature. Therefore, we say that we reject the null hypothesis and fail to reject the alternate hypothesis. All right. From there, and if your probability value is less than 0.05, meaning that at least one of the months have a different temperature, therefore you have to do a post-hoc test to ascertain which months are different in temperature from the other. And that's what we do at 2K HSD of our Anova, and we plot. Then we can plot. This is what we have come up with, and we have seen which months are different from the other. So what we take the mean temperatures for one month and minus the temperatures for the other month. And if the mean is 0, meaning that they are not different. They are not different. If you take my age and you subtract your age, and if the answer is equals to 0, then our ages are not different. They are the same. But if they are different, our ages are not going to be 0. And as I have said, October and May, the differences in their mean temperatures is not equal to 0. Therefore, they are not the same. Their temperatures are significantly different. The same way with May and August. And I've tried to explain why in our case here in Kenya, why it is different. May and June, May is quite hot and June is really cold around here. September and July, the same case. So that is it. That's when you do a post hoc test. You go further trying to ascertain which months are different in temperatures, mean temperatures from another. And this you can do for any other. And I've said this to HSD, what it does is does a t-test for each. I think next time we're going to talk about a t-test. So Anova is used to compare means of more than 2 categories. When there are means of 2 categories, we use a t-test, an independent t-test or a paired t-test. Yeah. And if you'd like to do something else, let's also do the same temperatures. Let's get Anova. Let's do Anova 2. Second Anova 2, and Anova 2. In this case, the command is AOV, and our formula, let us this time around take temperature, see whether the temperatures were different for the different stations this person used. Stations, and our data is equals to DF. Let's see. Station, I think it is station, just station, just station, not station. Okay, let's have a summary of that. So we want to see whether the temperatures were the same for each of every sampling station this person used. And whether the see that is okay. Now our p-value here is 0.83. This p-value is greater than 0.05, meaning that the temperatures for all the stations, for the different stations, were the same. So therefore, what do? We fail to reject the null hypothesis that says that the temperatures for the different stations were equal. There was no mean difference. There was no difference between the temperatures in all the stations. And now we can also do a 2K HSD, see what will happen, what happens. 2K HSD command of Anova 2. So you can see everything is above 0.05, but you test for any of the station 2 and 1 and all that. Let's plot that. Then you see how it comes up. 2K HSD of Anova 2. Good. Yeah. Every of the month, the difference in temperature is equals to 0. None is outside the 0 value of mean. The difference in the stations. So there was no mean temperature difference in the station. So as you can, one thing you can say that the lake has on average the same temperature all over its surface. So whether you are in Lake Victoria, whether you are in Kisumu or in Bukoba, the side of Tanzania, or in Uganda, the same temperature. So there's homogeneity of temperature in space. So you can conclude and say that there's a temporal difference in temperature. There's a difference in temperatures over time, but there's no difference in temperatures in the lake over. There's no difference in temperature over space temporarily.